Welcome guys, how is the energy today? Welcome to this brand new crystal clear session. Today we're diving into a seriously awesome topic, chemical kinetics. It's the whole story behind exactly how fast chemical reactions happen. I need your energy absolutely high today because we are going to print this concept directly into your brains, okay? Let's dive right into this explainer.
Here's our roadmap for today, and it's perfectly clear. First, the speed of chemical reactions. Then the factors influencing reaction rate. After that, the rate law, followed by integrated rate equations. And finally, temperature and collision theory. Master these 5 steps, and you are going to be absolutely ready to confidently tackle your boards and competitive exams. Let's start.
Before we even touch any formulas or complex equations, I want you to step back and look at the chemistry of our world from a macro level. Ask yourself a very basic question. Why does some reactions take literal years to finish, while others are over in seconds? Why does that happen?
You know those TV ads that say diamonds are forever? Well, the reality is diamonds are actually slowly transforming into graphite. But this process is super slow. It literally takes thousands of years. On the flip side, what happens if you drop a little bit of ink into a glass of water? It mixes instantly, right? That's a super fast reaction. But listen, in chemistry, our main focus is mostly on the reactions that sit right in the middle of those two extremes. Moderate reactions, like the Haber process for making ammonia, because we can actually measure and control their speeds practically.
And to measure that speed, we use a very specific term in chemistry, rate of reaction. Listen carefully to this. Rate of reaction simply means the change in concentration of a reactant or product in unit time. Basically, in a given amount of time, how many reactants are being consumed, or instead, how many products are being formed. It is that simple.
Just look at this visual shift right here. As the reaction moves forward and time passes, look at the first bar. The reactants are going down. Their concentration is decreasing over time. And in that exact same time frame, the products bar is shooting straight up. Reactants drop, products rise. That shift right there, that is exactly what the rate of reaction is.
So the obvious question is, who controls this speed? What are the variables that make a reaction fast or slow? Well, we have 4 main factors: nature and state of reactants, concentration of reactants, temperature, and a catalyst. Take a mental snapshot of this list right now. Let's actually understand a few of the most important ones practically. First up, how does the physical state affect things? Imagine dropping a solid iron nail into some acid. It's going to react, sure, but it'll be really slow. Now, take that exact same nail, grind it down into iron powder, and drop that in the acid. Boom, the reaction is super fast. Why does that happen? Visualize it. Powdered iron has so much more surface area. And the more surface contact those molecules have compared to a solid block, the faster they're going to react with the acid.
Okay, let's talk about the concentration of reactants. Honestly, the best way to intuitively understand this is what I call the samosa party analogy. Imagine, you and your friends are at a party, and there's a plate of 30 samosas right in the middle of the table. In the beginning, when there are lots of samosas, meaning the concentration is high, everyone is eating super fast, right? The eating rate is high. But as the samosas disappear and the plate gets empty, everyone slows down. I'm full, you have one. See? The moment the concentration of your reactant drops, the reaction rate automatically slows down.
Want solid, real-world proof of this? Just cover a burning candle with a glass jar. After a few moments, you're going to see the flame get smaller and smaller until it just completely goes out. Now ask yourself this reflective question. Why does this happen? It's because the oxygen inside that jar, which is a crucial reactant, was constantly being consumed. The second that oxygen concentration dropped, the reaction just halted completely.
Section 3, the rate law. Let's see how this is actually easy when we turn our physical observations into simple math.
Look closely at our differential rate law formula here. Rate equals K, which is our rate constant, multiplied by the concentration of reactant A to the power X and reactant B to the power Y. Now listen, there's a massive exam pitfall right here, so pay special attention, guys. These powers, X and Y, they are not always equal to the stoichiometric coefficients in your balanced equation. We strictly get these values experimentally. So please don't just look at a balanced equation in your exam and guess the powers.
Section 4, the math cheat code. Integrated rate equations are absolute lifesavers to help you avoid messy calculus.
I want you to stare at this table and just print it into your mind. This is your ultimate cheat sheet. Comparing zero-order and first-order reactions side by side like this makes memorizing them so logical and simple. Look at the half-life column for the first order, natural log of 2 divided by K. Notice anything special? It doesn't depend on the initial concentration at all. You will definitely see direct conceptual questions on this in your competitive exams. Visual comparisons like this are just literal game changers.
All right, let's zoom in from the macro-level math down to the microscopic molecular level with temperature and collision theory.
Lock this golden rule number 2 into your brain right now. In chemistry, it's observed almost everywhere that for every 10-degree rise in temperature, the rate constant practically doubles. It becomes 2 times. But what kind of magic is this heat actually doing?
This Arrhenius curve literally unlocks the secret. Look at it carefully. We have kinetic energy on the horizontal axis. As we heat up the reaction, moving the temperature from T1 to T2, the curve shifts to the right and flattens out. What does that actually mean? This beautifully shows that by adding heat, a massive fraction of molecules are suddenly pushed right over that activation energy barrier. They now finally have enough energy to effectively react.
But hold on, there is a massive misconception here. We often think that molecules just randomly bump into each other and boom, a chemical reaction instantly happens. But the absolute truth is, not all molecular collisions result in a chemical reaction. Think about it. What would happen if molecules just lightly bumped into each other? Absolutely nothing. They just act like random bouncy balls, hitting each other and bouncing right back, forming exactly 0 products.
For a chemical reaction to actually happen, you need an effective collision. And there are 2 strict rules for this. First, threshold energy. The molecules need to have sufficient hitting power and kinetic energy. Second, proper orientation. Visualize this like 2 fast-moving cars. If they just lightly sideswipe each other, nothing much happens. But if they crash head-on at the exact perfect angle, then the whole system reacts. Molecules are the exact same. They have to crash at the exact perfect angle to form products.
So, as we wrap up this session, I want to ask you one thing. Can you visualize these molecules colliding perfectly to form products? I am super confident that you now have the conceptual depth to tackle any kinetics question in your next exam. You should be feeling, wow, I finally understand this. From the samosa party down to the perfect collision angle, it's all crystal clear.
If you feel like you've absolutely mastered chemical kinetics today, boost up that reaction rate and hit the like button. Share this visual learning session with your friends, and definitely don't forget to subscribe so we can keep making these high-yield, tricky topics perfectly crystal clear for you. See you in the next explainer, and until then, keep visualizing and keep learning.